Thanks very much. So just for those of you who don't know me, I'm a computer scientist, a Haskell programmer. I've been in the Haskell community for a long time. As Sandra says, I'm a partner at WellTyped. For the last year and a half, I've been in this role helping IOHK as the sort of head of engineering for the whole Cardano project for IOHK. And my background is in computer science and specifically like programming language technology. My PhD was on Haskell and all that sort of stuff. It's been 10 years now we've been doing consulting with WellTyped. So this is intended to be a kind of an experience report, right? So I want you to ask questions all the way through, but there will also be time for questions at the end. So I've left, hopefully I'm leaving enough time to, but I can also talk and talk and talk. So do interrupt, either stick your hand up or just shout. This isn't intended to be about Cardano particularly. I don't want to tell you all the technical details about Cardano. This is supposed to be about what's it like to do a project like this, and what are the transferable lessons, other things that are useful for academics or practitioners that we can learn from this. What's worked, what doesn't work. But briefly, let me tell you a little bit about Cardano. So Cardano is a public blockchain cryptocurrency. So that means in the same category of things as Bitcoin and Ethereum and whatnot. And as I'm sure you know, there's dozens and hundreds of others. It's one of the technical differences is it's proof of stake, not proof of work, which means that it's not an environmental disaster, unlike Bitcoin or indeed Ethereum. You don't need GPUs and ASICs and mining. It's a different underlying cryptographic system compared to those proof of work systems. It uses lots and lots of peer-reviewed crypto research. IOHK actually has quite a number of academic cryptography researchers on staff or partnerships with universities. And it's just over a year old now, and it was, the public release was 1 year ago, and in fact the first code was more like 2 years ago. And I came onto the project about, as I said, a year and a half ago, so 6 months after the things really kicked off. And it's got a long roadmap. It's a very ambitious project. The current release is federated, and so the next thing is full decentralization. Any proper cryptocurrency has to be, or public, open one has to be fully decentralized, and that's the next big thing on the roadmap. We in fact have 2 smart contract platforms, which is perhaps greedy, but it makes a lot of sense. One of them is functional programming based, and the other one is traditional, and that supports different parts of the market. Native multi-currency support, blah blah blah. The list goes on and on and on of features that we are working on or that are in research at the moment. And if you're interested in all that stuff, there's a website which has the full roadmap going into the future and regular status updates. So the cryptocurrency space is very challenging to design systems and implement systems. Highly adversarial deployment environment is a nice way of putting it. I tell all the developers that everybody is out to get you. They really are. Any possible exploit, people will exploit them. And it only requires one weakness for hackers to discover a bug, or there's all kinds of potential ways in which these systems can fail. There are hard real-time constraints. These are not measured in microseconds, but they're measured in seconds, but they're nevertheless hard real-time constraints. The current proof-of-stake protocols are not particularly forgiving to particularly systematically missing deadlines. And if attackers can cause people to miss deadlines, that's bad. So hard, and that's an unusual setting. There's lots of concurrency, and as we know, concurrency is hard, and it's distributed concurrency, so it's even harder. Of course, software flaws can be fatal here. The system can stop, or money can be stolen. I'm sure if you follow anything in this space, you'll have seen news articles about smart contracts being useless and people stealing money and all kinds of things like that. You can imagine how easy it is for a single flaw to be completely destructive to these kinds of systems. because they are decentralized and distributed, we do not control, we as the authors of the code, do not control the setting in which the people running the code run it, whether they're doing it in a data center or on a Raspberry Pi or their laptop, or the quality of their Wi-Fi, or whether they've got a decent data center connection. And we don't control, we can't control the security precautions that they take particularly. And we can't really control the resources that they allocate, which is actually a very interesting one. It turns out that you really need to optimize for, you need to design for constant memory use in particular. Because think about what someone's going to do. They're going to run your code on their server, and then they will pick the size of Amazon server that corresponds to the amount of memory that your thing appears to use. But if your software, when it's under some kind of system attack, that suddenly doubles its memory requirements, that's going to be really bad. That means that all the nodes that were on the T1 or whatever kind of boxes are now going to stop. So you really have to then design these systems to have constant resource use, because you can't control people, you can't stop people from doing that. We don't control the data center operators. People will just do these things no matter what you tell them. So there's challenges like that. And the internet is not friendly to peer-to-peer distributed systems. We think of the internet as this abstraction where you can just open a connection between any two IP addresses, but that's not true at all. Most pairs of IP addresses you cannot open TCP connections to. But yet, on the other hand, if you have an IP address which people can open connections to you on, then everybody in the world can attack you as long as they know your IP address. It's a very difficult environment. But correspondingly, because there's hard problems, there's actually lots of opportunities for applying good computer science, which is actually what makes the space very interesting. I'm not particularly a cryptocurrency. I'm very risk averse. So let's put it that way. So I don't give out investment advice on cryptocurrencies. I don't follow that. But the underlying technology is actually very interesting. So in this space, delivery is very important. The users have sky-high expectations. And there's lots and lots of projects out there, all competing with each other, all with their fancy roadmaps, and telling the users that they can do everything and that they can do it quickly. And so then users want all of these promised features, and they want it now. And because a lot of the users come to these cryptocurrency systems without necessarily that much background in technology. They've read about it. And so they don't always have the sort of appreciation of how difficult it is to build systems and how long it takes to write software. And because there are so many, it's a very, very hype-intensive market, which I'm sure you know if you know anything about it. So yeah, there's lots and lots of competition and hype, and that makes it very difficult for people who are trying to describe what they can do accurately and deliver it, because other people are just going to say, oh, we can do everything, and we can do it now, whether or not they really can. So it's very difficult. Expectations are difficult. And of course, users expect the systems that you build to be reliable and to perform and to be secure, but they have very little way of assessing that, except when it fails. So it's hard for users to make comparisons between these systems. So we try to follow an approach where we will achieve these kinds of properties. But correspondingly, of course, that's difficult and it's time-consuming. And so yeah, correspondingly, delivery is important, but quality is also important. The opportunities for failure are legion. And not all of them are just software bugs. That's the sort of stuff that I think about all the time. But there's actually a huge number of ways in which these kinds of systems can fail to succeed. Not necessarily like catastrophic failure, but fail to achieve their goal, to be successful. So just running through some of them. So you can have flaws in your protocol design, by which I mean like the cryptographic protocol design, which fortunately I'm not responsible for. There's researchers who do that stuff, but you can easily make mistakes there. And that's why IOHK relies on peer-reviewed cryptographic research for protocol design. But you can easily implement those designs incorrectly, very easily. You can make all the typical software mistakes, the ones that we're all familiar with. Amateur cryptography is a great way to fail. I mean, no, it's a terrible way to fail. It's like amateur brain surgery. It's not a good idea. Don't do that. You can miss performance deadlines, and I talked about the fact that we have these hard real-time constraints. Missing performance deadlines, perhaps as systems grow or scale, that can be catastrophic. Because of the nature of the protocols, they often have these timing requirements. The system can collapse under load. I mean, not on this project, but as a consultant, I've been around and seen many systems where people just don't think about what is my back pressure strategy. How will it fail as I apply more and more load? Many people just don't think about it. It's very easy to miss that one and just to run benchmarks but not really think about how does the system achieve some stable state as the load increases. Failure to scale. You can design a system that's completely secure, works really nicely, but if it's not able to achieve the scale that users want to use it at, that the market wants, then the system can be limited. And that's to some extent happening to Bitcoin and to Ethereum. They're overloaded, and all current blockchain designs are fundamentally not scalable. There's all kinds of tricks that people play to make them more scalable. But what scalability at the moment really means is not using the blockchain quite so much, doing other things, not putting so much data on the blockchain. But no one has yet cracked the problem of genuinely making these things scale. I mentioned the internet is a difficult place to work in. Denial of service is a really big problem. I don't mean DDoS, just local, individual denial of service. If you can attack a particular node, and you know that one is the one that's about to create the next block or something, and you can do that systematically, you can destroy the system. You can destroy the productivity, the progress of the system. And that's something that is not. We don't commonly think about that in our typical programs, typical designs. This is this problem of asymmetric resource consumption, where I send you a message, and I've done very little work, but it causes your system to do quite a lot of work. That asymmetry can be is a very hard thing to. You don't get that just naturally. You have to design that into your systems, and that's difficult. That's a constraint that means that there's lots of off-the-shelf software that you just can't use, because those bits of software were not designed with that constraint in mind. So, for example, just off the top of my head, that means that we can't just go and use 0MQ, because 0MQ is designed for data centers. It's not designed for this adversarial environment. There's no statement in the 0MQ documentation that says that it's resistant to this kind of asymmetric resource attack. And that's fair enough. That's not what it's designed for. But that's the kind of thing that we have to worry about in this setting. Then there's other interesting kinds of attacks, which are completely not the software at all. Economic attacks, although there's a reflection of the economic attacks in the software. So, for example, if you know anything about Bitcoin, you'll know that it has this thing called a UTXO, which is basically a large database of the state of the system. And that grows over time, and they tend to keep it in memory for various reasons. You can have attacks on things like that, where if the amount of money or the resources that are used by the system is not properly compensated by fees that are charged to users, if there's an asymmetry there, then there's a way for someone to spend a small amount of money to cause you to consume a large amount of resources, which with corresponding financial cost. And that's a way that systems can be vulnerable to an economic attack. So you have to design these things such that the costs, like in the software, are each accounted for. So this is a lot like the kind of space and time analysis, asymptotic complexity analysis that we do in academia. You look at some piece of code and you say, well, what's the space complexity of this? And then in this kind of system, you've got to say, and I need to account for all of that and charge fees to the users correspondingly. And that constrains your designs. And then there's other things. Macroeconomic collapses, if you don't get your macroeconomic policy right, or if you get your governance policy wrong, maybe the system just fails to make progress because there's no way to make progress because there's no consensus. There's no social consensus about voting for changes. So there's all kinds of ways that these systems can not work, even if they're not catastrophic failures. So these things are multidisciplinary projects when done right. And you can't be an expert in everything. I mean, I'm, I guess, an expert in 2 of those things. So you really need to, these kinds of projects, you need to bring a lot of people together, a lot of different experts. And to IOHK's credit, that is what they have done. They have pulled together lots and lots of different experts. But that's a difficult thing. Even once you've got the people together, it's a difficult thing to manage different ways of thinking, different perspectives. So I think our entire industry has a problem. I mean, I observed it when I was a PhD student, and I still see it now as on the sort of industry side, that we have a problem between moving great ideas from academia into practice. And there's various kinds of reasons for that. I mean, some to do with funding and some to do with culture, but there is this gap. And there's various ways that people have tried to address it. I mean, a really good example is Microsoft Research. Microsoft Engineering, lots of programmers getting code out the door, and then PLT and other parts of research. And Microsoft, to their credit, decided to bring in something in between that sucks in all the great research and tries to push as much of it into products as possible. So that's one way of trying to bridge the gap. And IOHK actually does fund substantial research in cryptography, particularly, and also in some other areas, like certain bits of game theory and other kinds of things, mentioning all these experts that you need for these systems. But that gap can still exist, even within a single company, even when you've gone and hired or made partnerships with universities. You can't just chuck a paper over the wall to a bunch of developers and say, go and implement this. The cultural gap, the intellectual gap, the notation, the understanding, the gap is just too big. So what IOHK have done, one thing that I'm very pleased that I've been able to help and encourage within IOHK is the introduction of a group in the middle. I mean, it's a bit boastful to say it's like Microsoft Research, but it's on a very small scale. It's the same idea. It's trying to fit something in between to bridge the gap between these two areas. So it means that you have, because cryptographers are a special kind of computer scientist. As a computer scientist myself, I see that they're kind of on the far end of computer science from where I am. They use a different language, they use different notation. Their notion of proof is quite different to mine. So it's interesting to, from standing where I am and then also talking to the developers, you can see why there's this then really very large gap that you have to bridge. But it is possible by having people with the right expertise, putting them in the middle. And so the intention is to help that pipeline from research through to practice. And also to provide feedback to the researchers. Because if you go and talk to people in industry and say, why don't you use all this great research? They'll say things like, well, I don't understand it, or because the researchers don't think about practical problems. So part of the issue is that maybe sometimes there isn't enough application to feed back to the research to say, well, you need to think about this, you need to think about that. This is what you need to do to make it practical. You need to tweak this, tweak that. Or we have this concern which you would have never thought of. And now that you have thought about it, you can adjust to it. So it's not just a pipeline in one direction. It is a connection both ways. We have to balance quality and delivery. We have to, as I said earlier, we have to deliver things. Users demand it, and we need to deliver with quality. And that's obviously difficult, and there is a trade-off, but it's not an obvious and straightforward trade-off. It's not just a simple way of saying, oh, you cut more corners, or do things more sketchily and quicker. That doesn't necessarily lead to faster delivery, because, of course, as we all know, if you end up with poor quality software, then that itself is very slow and expensive, and it's hard to change and hard to fix. The actual time to first delivery can end up with spending half the time doing testing and fixing bugs late in the game, and that's very, very slow and very expensive. Fixing things early is much cheaper. We all know that, but that means sort of, to some extent, it means doing things right from the beginning. So there isn't a straightforward trade-off. It's a complex trade-off, and we have to think very carefully about how we do it. So the cryptocurrency space is a great application for formal methods. There's really a lot of problems in the cryptocurrency space where formal methods are really applicable. But it is still true that many formal methods are still slow. And that's not a criticism. That's actually a huge advance from where we were 15, 20 years ago. So we can actually apply formal methods now in practice in these kinds of systems. But we can't necessarily do it as the primary method. So we're taking a twin track approach of lightweight, semi-formal methods, which gives us quite a good balance of delivery pace and much improved quality compared to industry standard quality. And then in parallel, we can also have people working on using formal methods to sort of do the same thing again, but better. So you prototype one way, you explore the design space, and you follow up, and maybe you go a slightly different route using various different kinds of formal methods. And we've actually got several examples of where we're taking this kind of twin track approach within Cardano now. You don't need to know what a wallet is, but there is such a thing as a wallet. It's the thing that holds your money. So with the Cardano wallet, we redeveloped it following a sort of lightweight, semi-formal methods approach, lots of properties and quick check and whatnot. But we never proved anything. We just stated things and we tested things, but we never proved anything. But we are now following up with formalizing our previous semi-formal approach, formalizing it with Coq, and proving the properties that we stated. We stated a bunch of lemmas, and we tested those, but we never proved them. And now we're going back and trying to prove them. So we already had reasonable confidence, and this gives us even higher. Then we can actually produce evidence, a higher standard of evidence than we had before.
Have you found any bugs?
Have we found any bugs yet using the from the Coq formalization? I don't believe we have. No. Question over here.
What kind of properties can you prove with Coq? Can you measure space and time complexity? Or?
So I think okay. So the question is, what kind of properties can we prove with Coq? The ones that we would attempt to prove would be the functional properties. So our specification that we wrote for the wallet, it does talk about time and space complexity, but the properties that we would try to prove are the same ones that we tried to test using quick check testing of invariance and various kinds of functional value level properties. And those are the ones that we would also try to prove with Coq. I think we won't attempt to prove performance or space properties. We'll just rely on our normal kind of by hand asymptotic complexity analysis, and then you can go and do profiling and testing to confirm that what you thought was true does appear to be true, and that's probably the right balance. Another question over here.
How do you show refinement between the specification in Coq and your code?
How do we solve how do we bridge the gap between what we prove with Coq and what we have in the code? Yeah, okay. So we're not attempting to prove with Coq exactly things about the code. We are attempting to prove the properties in the specification itself. So the specification is described in terms of sets and predicate logic and whatnot. And it states a bunch of invariants and properties and things that ought to be true. So we're just proving things within that formalism. Now, the Haskell code, there's a Haskell executable specification, which is almost a one-to-one translation between the formal spec and the Haskell code. And it's true, we don't have any then formal proof about that we haven't made a mistake in that translation, except that we can run those same properties through quick check and check that we did not make any translation errors, which of course we did make translation errors, and we found them using quick check. So, but in the end, no, it's true. We don't have that's not going to the level of proving something about the Haskell code. It's proving something about the specification. You have to pick your level what degree of assurance do you want, and how much effort are you prepared to put in? Question right here, Chris.
So no bugs, got confidence. Have you developed anything else come out of this, like a deeper understanding from attempting to do the proofs?
Oh yeah, I mean we get a deeper understanding not by trying to do the proofs so much as just trying to write down the specification in the first place, and writing the properties and then checking the properties. That gives you a much better understanding, and that's the process by which you make the specification simpler. You achieve a simpler design, and then that's one of the really big wins of this kind of approach. All right, I'll move on for the moment. Yeah, and we're using other theorem provers and other things in other parts of the code base. Again, in this kind of, we're not kind of waiting for the formal method before we deliver, but the formal one, catches up. Okay. So one criticism of this might be that this is kind of the big upfront design approach, which people say, no, you shouldn't do that. You should be agile, 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 agile. And that's a somewhat legitimate criticism. But on the other hand, the way I look at it is that if you're building web systems with databases for your typical line of business application, there are many, many points in the design space that will work. And an agile approach will find some of them, and that's great. But if you're in an area that has a very complex design space, and there's only one or two designs that turn out that will actually self-consistent and work, then that kind of just try something and then build another thing on, then build another thing on, iterative, is not necessarily the great approach. So the approach that we're taking is solve the hard problems first and try and find that point in the design space that is going to work, and then spend more time going into it. Because otherwise the danger is that you have to backtrack the wrong way. You have to backtrack after having done a lot of work already. So one of the tricks is to go for the highest level of abstraction you can get away with, and do your design at that level while it's small enough to fit in your head, and then try lots of alternatives, and that's a much cheaper approach. You're solving problems up front that would later be very costly. So I'm going to go just through little examples of some of the semi-formal approaches that we take. So I already talked about the wallet. As I said, we wrote this precise specification. Where is it? Here it is. We then published, and it goes on and on and on and on. But one of the nice things about it is that we end up with a specification that fits on one page. I don't expect you to read this, but the point is that does fit on one page, so which means it fits in your head, and it fits in many people's heads. So that means that you've got sharing of ideas. Many people can look at it and go, yes, okay, that's right, or I don't think that's quite right. So it gives you more brains to review these things. This stuff is very straightforwardly translatable into Haskell, and that's deliberately so. We design these things in such a way that they have a straightforward computational interpretation. But they're also something which other people can understand. I mean, mathematicians and other researchers can understand. Because one of the problems that used to be was that they just couldn't understand these reams and reams and reams of Haskell code. So they couldn't really tell whether what the Haskell code did was what they thought it was supposed to do. And this gives you something in between. It's a meeting of minds between programmers and mathematicians and other researchers. Because everybody knows set theory and logic, right? This kind of approach gives you a very easy way of testing with abstraction. You have your executable specification, which is an example from the last slide, and you have your real implementation. It doesn't have to be a pure function, but the same idea works. And you need a way of saying, how do I go from the complicated real thing to the simpler one, the simpler formal executable version? Because the key thing is that your executable, your higher level one has to ignore details that aren't important. That's what makes it simpler. So then you have this abstraction function that goes on to other. So then, many people here would recognize this as a commuting diagram, and you can test this with quick check, starting in bottom corner if you abstract and then run it through the spec and go through the real implementation and abstract. And you do that for any sequence of operations on the things, you should get the same result. And that gives you a very nice way of checking that your real implementation does do what the abstract specification does. And this works very nicely with quick check using arbitrary generators. And it gives you really good evidence and really good coverage and quality of testing and assurance. We found interesting and subtle bugs this way, which we would have probably never found otherwise. And of course, the other big win from going for this kind of approach is just the reduction in complexity. If you spend a lot of time making your spec fit on one page, then your implementation can also be not all that large. You've made a simpler design. And that is massive as a saving. The thing that kills you in these systems otherwise is accidental complexity. Another example of one that we're working on right now, as I said, there's lots of this big long roadmap with Cardano, and there's lots of new features in the ledger layer of the system. And so we're currently kind of prototyping those ledger features, sort of on virtual whiteboards, because everyone works distributed, and then turning them into LaTeX. And writing them down in kind of formal notation helps you communicate it. If it means it's small enough to fit in people's heads and review and have lots of people think about it. And it means that many problems can be identified and resolved early. So for example, we start off with that kind of stuff, just on a whiteboard or someone's virtual whiteboard. I don't expect to go into the details here. You have to pick the right level of abstraction for these kinds of specifications. You have to have an abstraction that's high level enough to keep it small, so that it can fit in people's heads. People aren't prepared to go and review reams and reams and reams of detail. They just won't do it. But it has to be low enough level of abstraction to capture interesting things, to capture sometimes operational concerns, because we have operational concerns about space complexity and time complexity and these kinds of things. So for example, with the ledger rules, the ledger is the data that goes on the blockchain, and we can see it basically as being a kind of fold L over the events or the objects on the ledger, and it's a state accumulation fold L style. So the obvious way to specify that is by a state transition relation. And if we do that in an operational style, where we say exactly what state we are accumulating and updating, it makes it very easy to translate into code. And it means that at the level of the spec, we can think about it and say, right, what's the space complexity of this? How much information am I retaining? Is that linear in the size of the blockchain? Oh no, that's not going to work. Let's do something different. Lets you change those designs early on, while the spec is still small and manageable. So then you end up doing this kind of stuff. You turn it into LaTeX, and then you just go through lots and lots of iterations of design reviews with enough people. Enough brains then start to see the problems. Haskell is not a silver bullet. Everybody knows you can write terrible code in any language. So it's not so much the language, but the approach. I've basically already said all this stuff. But Haskell does make this kind of approach much easier to do. If you're taking applying lots of proper computer science, it's a whole lot easier to do in a language like Haskell. And there's a social, cultural aspect that Haskell people who've been keen enough to go and learn and use Haskell, are culturally ready to take this kind of approach. And that's very important, because you need buy-in from everybody to take a somewhat more formal approach to these things. And of course, the ability to go from a specification to an implementation easily, to turn the mathematics into code is a great advantage. And the ability to write once and both simulate and execute is a massive win for testing and therefore for quality. You can have a single, maybe if I have time, I'll show an example later of cases where we can have a single implementation of something in such a way that we can both execute it for real, it is the real implementation, but it also can be interpreted in simulation, in a pure simulation where we can get traces and then write quick check properties over those traces. And that's the way that you get really, really good quality. And you don't have to do two versions. And, it's the same version. I don't think I'll go through those examples. Oh yeah, let me just say with this one, because I was just mentioning about the, let me jump back one, about this idea of simulation. I mean, this is in many ways an obvious idea, but the point is it really works. So one of the things that we have to do as part of making the system distributed is you have to have network protocols. And as I said, we can't just reuse 0MQ because asymmetric resource attacks and all the rest of it. So we're doing some of our own protocol development. And the traditional approach to that is that you start writing low-level specs about what your wire format is, and et cetera, et cetera. And you just start writing accept calls and socket calls and doing it directly in I/O, directly with the TCP or whatever API. And that's hard to test because you have to set up real systems with real sockets and kill that connection at the same time as doing this. And it's very hard to test the corner cases if you can't abstract over the low-level effects. So the approach that we're taking is a simulation-first approach where we abstract over, are we in I/O or something that we can simulate? And then you can iterate that design without having to set up multiple machines. You can run it all in a simulation. You develop your quick check properties in parallel with your prototypes. They go together because they inform each other. And you can do that even with concurrency and STM. And that's the approach that we're taking in particular for our network protocols at the moment. So we have a pure simulation of STM, and then we use that for the quick check properties. It tells you that if you put this blockchain in over there and you run the synchronization protocol for enough steps, then you get the same blockchain out over there. And great, that's. And you can also then set up difficult corner cases where things are expected to fail, which are very hard to set up in the real world with real TCP connections and multiple machines. There's also some opportunity to simulate performance with this kind of simulation approach. And in these big distributed systems, the large-scale performance is very important. And you don't want to leave it to the end and discover, now that you've implemented everything, and then you set up a big real-world test that it doesn't scale or doesn't meet your timing requirements. And to some degree, I mean, it's simulating. You can never get brilliant accuracy, but to some degree, you can simulate performance in this kind of simulation. And there are actually compositional ways of doing performance simulations, which we are trying to apply. Although it's actually rather interesting. Well, it was new to me anyway. We've got some networking consultants who have a really nice compositional algebra for doing performance measurement and analysis, which is very interesting stuff, which we're trying to work into our system. So just as an example, this was a type class that captures the basic STM API and forking, of course, and then that means that you can write your protocol implementations abstracted over this type class, making use of all the STM API, and then obviously I/O and STM are then an instance of this thing just directly. But our sim I/O with its corresponding STM monad are also an instance of that. And that's one that we can run, it's a pure simulator, very much in well, if you've read any of the papers about, it's the classic style, for those of you who know it. But in this case, using the STM API. And that works very nicely, giving you a pure trace that, well, in this case, we run it in ST. And we can use probes to get typed traces. I mean, that's an untyped trace, but I've not shown you. There's also a probe API where you can say, I want to be able to see things coming in here and see them coming out there, and then in the trace that you get out afterwards, then that's how you write your quick check property to see, did the execution run the way you wanted? Yeah, I will stop here, and yeah, questions.
Okay. Thank you.
Question back here? No. Further towards the back.
So how much do you test the trusted, or how much do you look at the trusted code base, like the Haskell runtime system? This is something I normally never worry about, but when you're handling so much money, that would be the attack factor for a as a memory managed language, right? So how much do you test that at IOHK, and have you found any disturbing bugs in Haskell's runtime system?
We haven't yet got to the level of having to worry about that. There are bigger problems that have to be solved first. I mean, we don't have. I mean, I said we have hard real-time constraints, but they're measured in seconds. We don't really have problems with like incremental garbage collection or that kind of thing. I think my intuition is that so long as we can solve the that we have good control over our asymptotic complexity, that we're not going to be killed by the latency, pauses in the GC, that kind of thing. But that may be a problem that we have to come to a little bit later. But not yet. There's definitely bigger problems.
Okay. One more, perhaps?
Question at the back over there?
So this is more a comment than a question, sorry.
Yeah.
But it's a supportive comment, which I think there's this type of process is demonstrated to be successful in different environments. So in the development of the SL4 verified microkernel, which is first fully verified microkernel, we also proceeded from a Haskell model. So that first was an executable specification of the behavior of the operating system, and then that was used both for abstracting it into formal properties, in Isabelle in this case, and as a blueprint to write the C code, which is the actual implementation which is linked up in the formal verification. So I think using Haskell and formal methods in this linking capability which you described is really a very good approach.
Yeah, so that if you're going for formal methods that use Haskell and quick check and testing and iterative development first before you, and then in more typical situations you can actually just deploy that, and that's usually fine in most in most applications that we have. But then also, there's the opportunity to follow up that kind of approach with more formal methods. I didn't have time to go talk about the lessons about what doesn't work, but I'll post my slides, and you can also ask me questions afterwards. What's difficult and etc.
All right, then let's thank Duncan again.
Thanks very much.